Okay, so now in this example here, we've got the series of natural log of n over n squared. And so here's the thing, what should we compare this to? Should it be 1 over n? 1 over n squared? Well, how do we figure this one out? Well, let's compare the natural log of n to something that we know. Let's compare it to n, right? So if we compare this to n, let's say we want to compare it to n over n squared. Well, we know how do I write this? So we know that the natural log of n is less than n, right? For all n, for all positive integers n. Okay, that's true. So that means what? The natural log of n over n squared would have to be less than n over n squared, which equals 1 over n. Right? Okay, so now, we're going to compare this to 1 over n. So let's compare it to so we're going to compare it to the harmonic series. Now the harmonic series, we know, diverges. Okay? So let's see what we get when we do the limit comparison test. So let's take the limit as that approaches infinity of the ratio, and we're going to do the natural log of n over n squared all over 1 over n, which is going to equal the limit as n approaches infinity of what? This is going to become natural log of n over n squared times n over 1. And so what happens? This n cancels with one of those n's, and we get the limit as n approaches infinity of the natural log of n over n. Okay, so now here's where this comes in handy, because we know that the numerator here is always less than the denominator. So that means that this limit as n goes to infinity is going where? Well, n is growing much faster than the natural log of n. So but it's still not obvious, right? We can't do some of the techniques that we did before in the last two examples. So here's what we're going to do. Let's compare it to a function. So we know that the natural log of x over x behaves the exact same way, and they have the same values at the positive integers of n. So let's do the limit as x approaches infinity of the natural log of x over x. And so this is a continuous function, right? So we know that as this goes to infinity, what do we get? We get infinity over infinity. So that gives us one of those indeterminate forms. So then we could use L'Hopital's rule. So by L'Hopital's rule, what do? We take the derivative of the top and the bottom. So we take the limit as x approaches infinity of the derivative of the top. And what's the derivative of the top? That's 1 over x. And the derivative of the bottom is just 1. So we get the limit as x approaches infinity. Really, this just becomes 1 over x, right? If we simplify it. And so the limit goes to 0. Okay, so my suspicions were correct. Now, here's the thing. Since it goes to 0, what does that say about our case? Remember, in the case, we want to make sure that we have things that are met, right? So this is the case 1 that I said, where the limit does equal 0. Okay? Now, but here's the thing. This is 0, but the harmonic series diverges. Now, if this converged and we had 0, then we could say that this converges, but this diverges. So in this case, we cannot determine anything. So this is, what's the word that I want to use? The result is inconclusive. That's the word I'm looking for. So we can't determine what the result would be. Okay. So what do? Well, let's compare it with 1 over n squared. Okay, so now what we're going to do, it didn't work the last time, it was inconclusive, so let's use the series n equals 1 to infinity of 1 over n squared. Right? Well, obviously this converges, right? Okay, it's a p series where p is greater than 1. So now, let's do the limit. As n approaches infinity of the ratio of these two. So again, we're going to take the ratio of the natural log of n over n squared all over 1 over n squared, which is going to give us the limit as n approaches infinity of what? Well, this is just going to become the natural log of n over n squared times n squared over 1, and so these are going to cancel, and we get the limit as n approaches infinity of the natural log of n, which equals infinity. Okay, now, in this case, we've got infinity. But, in this case, since this is infinity, in that case, it would be great if this diverged, because then we could say this one diverges, but this is going to infinity and this converges, so therefore, again, it's inconclusive. series that is between the two that we tried. Okay, sometimes it's trial and error. So let's try another one. Let's try the series n equals 1 to infinity, and let's do 1 over n to the 3 halves. So we tried 1, we tried 2, let's do 1.5. Okay, so again, let's take the ratio and see what we get. Okay. So the limit as n approaches infinity. So now we're going to do the limit of natural log of n over n squared, all divided by 1 over n to the 3 halves, which again is going to give us the limit as n approaches infinity, and we're going to write this as the natural log of n over n squared times n to the 3 halves over 1. Now, this is going to cancel with this, and it's going to make this into the square root of n. Okay? So this is just going to give us the limit as n approaches infinity of the natural log of n over the square root of n. Okay, now, what do we do with that one? Okay, because square root of n doesn't grow as fast as n does. And the natural log of n sort of has a similar type of curve as the square root of n. So, it's not as clear as where this thing is going. So let's use a real valued function again. So let's take the limit as x approaches infinity of the natural log of x over the square root of x. Now here's where, again, this is going to give us an indeterminate form. It's going to give us infinity over infinity. So now we're going to take the derivative of the top and the bottom. And by L'Hopital's rule, this becomes the limit as x approaches infinity of what? It's going to be 1 over x over, well in this case here, the derivative of the square root of x is going to end up being what? 1 over 2 root x. Oh, hold on a second. Yeah, that's right. Just want to make sure that was right. Okay, so now we can cancel things out. And so this, well, let's write it this way. So the limit as x approaches infinity, and this is going to be 2 square root of x over x, right? And so now we can cancel those x's, because then this is going to become the limit as x approaches infinity of what? It's going to be 2 over the square root of x, which goes to 0. Okay, now, well, we're done. So because now this goes to 0, which means we're in the case that if this converges, then so does this. Well, this does converge, right? This is a convergent p-series, right? P is greater than 1. So this is a convergent p-series. And so since the limit of the ratio is equal to 0 and this series is convergent, then this series must be convergent by the limit comparison test. That's it. Have a great day.